Hey guys, so let's go briefly over this universal gravitational law. I have the New Jersey site on one computer because I don't know how to do this otherwise, and I'm just reading, not really reading, but I'm just summarizing those slides. So if you need that, obviously you can go on the New Jersey site. I can repost the link, and you can find the slides that I'm talking about. So the very first thing I see is that they are talking about the law of gravitation. Okay, so one thing that I wanted to point out is that they write this force as a force gravitational, okay, as G, obviously, as you know, m1, m2 divided by r squared. So this means if I have a mass here, m1, and a mass here, m2, okay, this is the distance between the two nuclei. Okay, this is r. So r squared is the square of this distance, obviously. Then you will notice that if I write the force like that, this is just a scalar quantity, right? If I want to make sure that you understand or people understand, right, that I'm talking about a vector instead, obviously I got to show the vector on top of the symbol for the force. Then I will write this as g m1 m2 again divided by r squared, but this is still a scalar quantity. In order to make this a vector, I got to give a vector right here, and the vector is r. Now I got two choices. Either I write r like that, but if I write r like that, this means that I will have to find the magnitude for r. So instead of showing the arrow, okay, by convention, okay, I will show a hat. Every single time you see the hat, I hope you remember this, okay, I'm showing a vector that has a magnitude of 1, right? I think we talked extensively about this. Okay, so this is also called univector. Okay, because it has a unitary magnitude. Okay, so the hat, every single time you stick the hat on top of a letter, this just means that you're talking about a univector. Now r, the reason why this is r is because the force is radial, right? Because if I have a mass here, okay, just like for charges, this mass will create a gravitational field. Okay, just like a charge will create a electrostatic field, the mass will create a gravitational field. Okay, but for the charge, okay, if this was q1 positive, for example, we had the electrostatic field like this. Remember, so it was radial, and basically this meant that wherever in the space I put a different charge, another positive charge, this will be repelled, okay, in any place I put it. So if I place it here, this charge q1 will exert a repulsive force. Obviously, if instead, and this is by definition what the q looks like and goes forever, right, obviously becomes less strong and less strong as the distance increases. Okay, for the electrostatic field works the same. Okay, remember also that if I have a negative charge, this will be attracted anyway, right? Because at that point becomes a field between the negative and positive, right? So those two charges will attract each other. Okay, so for the gravitational field instead, for some reason, okay, there's the still radial field, okay, and is always attractive. Okay, so whichever mass I place here will be attracted. This mass m2 will attract m1, and this mass m1 will attract m2. Wherever I place a mass, there will be attraction between the two masses. Okay, why? We are not really sure about that yet, even though it's something that everybody experiences. We are not really sure why this happens. And there's still this idea of creating this universal law. that includes both electrostatic and gravitational. But again, as of now, we can't do anything. So remember that because those two masses, okay, you can have M3 here, okay. If I'm talking about interaction between M1 and M3, then I'm going to have force between 1 and 3, okay, and this is going to be the G M1 M3 over R squared, okay, and then the distance between them radially, right? Obviously this is the same as the force exerted by 3 on 1, okay, because I just have to how do I say, commutate, right, those two masses, and I will get the same intensity of force. So with that respect, this is still Newton's third law, but whatever. What is this value G? Well, G is a universal constant and is 6.67 times 10 to the negative 11. How would I know the units? Well, if this is Newton, this is meters, this is kilograms, this is kilograms, obviously Newton, units for this is Newton. I'm sorry guys, my grandchild is loud. So this is Newton meter squared over kilograms squared. That would be the unit for G. Okay. Other than that, I think if you want to know about this, there's an experiment that has been made. I don't see it in your slides here anywhere, but there's an experiment that was made in order to understand that this attraction exists and can be determined experimentally, in particular the G. So you can have basically a string, let's say, whatever, and here you can place, now I don't remember exactly the setup, but it's kind of a rod and two spheres here, okay, and then somewhere up here there should be a mirror, or you should have a mirror somewhere, and then there's a different mass positioned here, just like a tester, for example, okay. So let's say this is M, this is M, those two masses are the same, and this is a different mass, okay. This is basically a torsion apparatus, and so a torsion balance, okay. And according to this experiment, basically, again, I don't really remember where the mirror is going to be, but basically with the position of a strategic mirror somewhere, you can see, okay, that those two masses, or you can just look, and you can see that basically there's a rotation here because this is a torsion, okay. Or if you want to leave this one in place, this is the angle that you're looking at, whatever you prefer. So as time passes, those two masses, okay, will try to get closer to each other, okay. So let's put here the big mass, okay. So you will see that this mass rotates in order to get closer to this, okay. Obviously for masses, because we are on the earth and stuff, this will happen very slowly, okay, but you can basically record the rotation of this angle, okay, and you can see that this happens, and this is the Cavendish experiment, okay. Other than that, what else is there? Then okay, you have questions there. Then gravitational field, we just said what happens there. So you will see that wherever you place a mass, this is going to happen, okay. This attraction is going to happen, so you can place the mass there. So this means again that this mass, okay, has this gravitational field everywhere around. So wherever you position a mass, there is going to be attraction. Then so for what we care about, okay, is that if you are, for example, here on the earth, okay, and this is you, okay, so this is the center of the earth, so this is the big mass, and this is you right there, okay, with a smaller mass than the earth. So between, how do we calculate a ton of stuff? So between you and the Earth, there's always, of course, gravitational attraction. So Fg gravitational is equal to the big G and then the big M, small m r squared, where again is between the center of mass of you and the center of mass of the Earth, unless you have different data. And in that case, you want to calculate, for example, the distance between the center of mass and the surface of the Earth, or on top of the Everest mountain, whatever you prefer. But anyway, this is the value for your gravitational force. This is equal to mg. Okay, so according to this, so this is what we know according to Newton that the equation looks like, right? This is your weight, mg. So at this point, by comparing those two expressions, we can remove m and we can solve for g. So knowing the mass of the Earth, the distance between you and the center of the Earth, but in particular, okay, if we consider this as the r, because it's so big compared to my especially little height, right? So you understand that 70 centimeters don't do much, okay, compared to the whole kilometers of the radius of the Earth. So at this point, this distance here becomes not significant at all. So this could be just this distance here between, so the radius of the Earth. So at this point, because of g, because of m, and because of r, you can calculate the little g, okay, which is the 9.81 meters per second squared. That is the value that we know about. Now you also understand, because now you're a big boy, that if I consider a mountain, okay, and I'm standing on top of the mountain, sometimes this other distance can be significant, okay, to add to the whole radius of the Earth. So that's why this value actually changes slightly, okay, according to your location. So this is at sea level, okay. So sea level means basically where you're considering the whole radius as your only distance, okay. The higher you go, obviously, the more this value will change, okay. And if this is bigger, then this is smaller. So obviously, the higher you go from the Earth, okay, the smaller gravitational pull you will feel. Until you, for example, are out in space, so very far away from the Earth, and you feel nothing. So other than that, there are again questions. Gravitational field of a sphere. This is not necessarily something that they might ask. It becomes more important when you have charges, okay. But one way that they are showing this on the slide is that if this is basically what we have just found, gm over r squared, okay, and the univector, this is the g vector, okay, this is true, okay, every single time we are actually out of the Earth sphere, right? So for r bigger or equal to the big R, okay. So if this in particular, let me change this. So we are calling this r if little r. So if I'm talking about a distance here, which is big R, okay. So if this big R is bigger than or equal to 2r, basically this exists, okay. If I am inside the center of the Earth instead, okay, so for a distance r smaller than the little r, so inside the center of the Earth, g is equal to 0, okay. Then there are other things I don't think we care about. Then there are also, so I'm just scrolling. Again, I've never seen questions of this kind. Like, again, if you scroll there, you will see what I'm talking about. But I've never seen questions of that kind in the AP exam, but I have seen it when we are talking about charges instead. If you have a spherical charge, then yes, all this becomes substantially important. Gravitational gravitational potential energy, we know that the delta U, the change in energy, is the U final minus the U initial. And this is basically the work done against gravity. Okay, so this is the negative integral between R initial and R final of your Fg dr, in this case, because R is our variable. If you consider x, then it becomes dx. So this means that the change in potential energy is equal to the negative integral between R0 and R final of your minus g m over R squared dr. Okay, so when you solve the integral, whatever, basically you find, right, that this is equal to, like we said already, m over R. In general, if you go for the solution of your thingy instead of being just the generic R, okay, because you got to substitute this one between R0 and R final, this becomes instead, delta U becomes instead minus GMM R final minus GMM R initial. Okay. And you can organize this in any way you want. So in general, we said potential energy equation is just minus G M over R. The graph for the potential energy, okay, looks like this, okay, where this is R and this is your gravitational potential energy. Why are we writing this on the bottom here? Well, because we have the negative sign, obviously. Other than that, what else can we talk about? Okay, so if we actually, okay, so let's do this, because actually this is what I think you were asking the other day. So delta U is equal to minus GMM, and then I'm having here 1 over R final minus 1 over R initial, right? I can write this as bring everything to the same denominator, so minus GMM, and then this one I can write it as R final R0 one sec, let me do one step at a time. Okay, so this is, so I want the same denominator, so this is going to be R final R0, so this is R0 minus R final. Okay, so this that I'm chopping badly, okay, so this is basically, okay, I can consider this value here, our final minus, so this is a negative sign, so I can replace the negatives, I can multiply everything by -1, so that you see every step there. So GMM, and then this becomes our final minus R initial over our final R initial. But our final minus R initial is equal to your delta H usually, right? And if I am considering instead the distances, okay, our final, our initial as the same distances basically, okay, because we are at the surface of the earth, then our final is almost our initial. Like I said, my little height doesn't change much, so I can say that our final R0 is equal to R squared, okay, and I will call this still the radius of the earth, for example. Okay, so delta H also is a lot smaller. Any delta H as I'm falling from my window to the ground is still a small distance compared to the radius of the earth. So at this point, basically what I can do is I can write this equation here as a GMM and then this will be the delta H over R of the Earth squared. Okay, so this is usually what we consider, okay, as, and we round, okay, as a m, my mass only, okay. Let me do one more thing in such a way that, again, every step is in place, okay. So the big M is the mass of the Earth. The G is always the same, okay. The radius of the Earth is always the same, so I can factorize, let's say, this one, okay, and then I'm remaining with M and then delta H, okay. But this quantity here in parentheses is G, right? The 9.8. So that's why this is mg delta H. I hope that this makes sense. Okay, so, and this probably will also make you understand why Drake, I think that was you were confused about the different forms of the equation, because you can have delta H on top, but you can have the R on the bottom, because at this point you're dealing with the shortcuts, right? U, we say, is mg delta H, but we also say that U is equal to GMM over R squared. So obviously you're saying, well, is the R and the numerator or denominator? Well, that's why it's so important to understand basically what we are talking about. If you're talking about G, okay, the gravitational law, and so you're comparing the G on the Earth, then you know that the GM over the radius of the square of the Earth, okay, this is equal to the little g, okay. So if those are all the premises, then you can shortcut your gravitational law, okay, and write this expression here. But if instead you're dealing with distances, okay, that are comparable, and you cannot just do this, okay, then this shortcut is not valid anymore. So at that point, you have to consider your total equation there with a real distance between the two masses. Okay, so this equation is super important either in gravitational situation, okay, again, when you're dealing with planets, stars, stuff like that, okay, or when you're also dealing with molecules, okay. If you have, for example, a cation and an anion right there, okay, so those two charges, okay, they will have some kind of potential energy on their own, but when they are in proximity to each other, okay, then becomes a situation like this, okay, now so majestically distant like a planet and a star, okay, but significantly close, but the relationship, I want to say, the ratio is almost the same due to the small sizes of those cations and anions compared to stars. Okay, so those are basically the two scenarios when you will use this equation here rather than the MGH. Okay, other than that, I think that you should be okay. Conservation of energy, okay, whatever. So there are Newton's law that I don't know if we can wait a couple of days to talk about this, but this is the basic scenario for your gravitational stuff. The other thing you have to remember that once you're circulating, so if you have a star and you have the planet and you're circulating, okay, then you have your force. There's always force between those two masses, right? So there's always this GMM over R squared if this is R, okay? But because of the circulation thing, okay, according to what is revolving around what, this is your M. For example, if this is the star and this is the planet, So this is the little m, then this is mv squared over r, right? Because m is what is circulating and you're assuming the star stuck in one spot. Okay, so now you have this situation here when you have to consider those accelerations. Okay, and remember, because this is an acceleration anyway, not the g, the little g that we know about, but it's still an acceleration. So if you consider this scenario here, then you have the g m over r squared, we said, is equal to mv squared over r. I can remove the m. Okay, so those are r's. Okay, and this is a v instead, so I can remove the square and the r. So now I can say that v is equal to g m over r. Okay, and this is square rooted, and this is the v of the orbit. Okay, in this case the velocity of this, so the orbit that this planet is doing. Okay, so also there's well, let's stop right here, and then I'll post another video instead about those 3 Newton's law, the gravitational laws. Okay, well, we will talk about that. I'll post a different video for that. Okay, I hope that this makes sense, guys.